Okay. So recording with microphone. Not on yet. Hello, hello, hello. Is it on now? I think it's on. It's very quiet. Okay, I think as I talk louder. So it's on at 3:05 for documentation. And so let's get to gravitation. And there's the electrical buzzing. And now, red light, it's gone. 3:05. Okay, so there's that test. Okay, so we'll focus on the physics here. So new packet, page 1. It's on the shorter side, if you will, compared to the rest. Gravitation is not a huge topic, but it is a topic that maybe, I don't remember the exact percentage, but in 5 years, the first 5 years, only one free response was asked about it. This was one we saved for the end that if we didn't have time for it, oh well. But here we have 2 days plus whatever we have right now. So please direct your attention. Yes, back group? Because the exam is next Tuesday, April 26th. Okay, that's y'all. And so get serious, right? It's our last topic though, so celebration on that. And so what is gravitation? So previously, all year long, we said gravity is equal to 9.8. We rounded to 10, right? But it was always 9.8. Yes, it's down towards the center of the earth, but it was 9.8, 9.8, 9.8. Well, what about the astronauts in the International Space Station? Is it 9.8 for them? No. Back group, I don't want to yell because then I end up coughing and then it's not productive for anybody. My mic is not working, so please put your head down if you don't want to learn physics, okay? I don't like saying that, but there you go. So International Space Station, a lot of times the common non-physics class, they say, ooh, the astronauts are weightless. True or false? False. They still have weight, but is it the same weight that we have here? No. Now, why are they floating if they're not weightless? How does floating happen? Well, there is a lower gravity. So that 9.8 for you and me right here, right now, it's a smaller number for them. But the key to it is they're falling towards the Earth, the same as their container, the International Space Station. And so they're falling all the time, but they don't feel it, right? They feel weightless because gravity is so low for them. And somewhere in here, we'll calculate the approximate gravitational acceleration, not 9.8, but what would theirs be? Question? Yes, it's falling. Well, the moon has its own gravitational field, so they don't necessarily float midair. They're just coming back to the surface of the moon at a lower rate. So the moon's gravitational acceleration is 1/6 that of Earth. Zach? Yes, Ganesh? Yes, so the way AP would code it, and I think we've seen one previous where they want you to ignore all effects of gravity. They'll say it's in far, far away from any significant masses, something like that. But yeah, if you go to the moon, that's a significant mass. It has its own gravitational field, okay? And so Earth has its own gravitational field, but here's the thing. It's not a constant 9.8. This is the way we're going. It's 9.8 for near distances. So notice I put a picture here, okay? It's a graph, it's the Earth, it's an apple. So look at the x-axis. It talks about when an apple, hold your question, hold on. Okay, I only get 2 days plus. So just hold questions for a second. I might answer them. So if I'm near on the surface of the earth, I have an apple. It says at 1D, that's 1 radii of the earth, maybe the apple weighs 1 Newton, right? So that would be your mg. That would be your, whatever the mass is, times 9.8. But then notice when it takes it to 2D, when I'm twice the earth radii away, we know a little bit about this effect. Magnets, have you ever played with magnets? The further magnets are apart, does that mean a higher or lower force? Lower. There's less repulsion and attraction. Now here's a big difference. We don't study magnetism, but gravity doesn't repel. It only attracts, okay? So whenever we talk about forces of magnets, just as a comparison, think about the attractive force, okay? But at twice the distance, you would expect a smaller force. And if you think too quick, twice the distance, half the force. But it turns out to be a fourth of the force. And you can keep it going, 3 distance, 4 distance. But at the end, you see that the gravitational force is proportional to the inverse of that distance of separation squared, okay? And that's an important part of the equation. That gives us the curve in the graph. And if we go back up to the top left of page 1, we get our new equation. And this is used for gravitational force for objects at a far range, a far distance. If it's me dropping a pin right here, right now, mg will do it, right? Mass times 9.8. But what if I go up to the International Space Station and drop a pin, right? It's going to have different motion. It's going to have a different force. Oh, and by the way, the other thing, how come the astronauts and how come the International Space Station doesn't just plummet into the Earth? It has that tangent velocity. It has that inertia, that tendency to still go forward. And so it's still falling, but that falling just gets it a nice orbit. We'll look at orbits coming up, okay? And so here's Newton's law of universal gravitation. And so we'll talk about Kepler's laws as well later on. This is not Newton's 4th law. This is separate, okay? Universal gravitation, it doesn't just apply to Earth. You can take it to the moon. We can talk about other planets, Jupiter orbiting around the sun, right? We can talk about 2 objects in space. Like you said, maybe it's far away from planets. Maybe one's orbiting the other. And so what is this new equation? Well, one of the big differences, instead of little g, we get a big G. This is a constant, but it's not 9.8. Someone flip over the formula chart to the constant side. You do not have to memorize capital G. What is capital G equal to? Right. And at first glance, you're like, man, that's a small number. Can't we just neglect it? But if you think about it and how we're going to be using it, we'll be using mass of planets. And not that it's on the formula chart, not that you have to memorize it, but the mass, let's stay with Earth, is 6 times 10 to the positive 24th. Okay, and you can see in the equation, mass is important. And so you've got a really big number, a really small number. They're both significant, okay? All right. And so that's big G. And then we see little m, big M. I like to view this as the smaller object and the larger object. But just so you know, depending on what book you read, video you watch, you may also see M1 times M2. Same thing, big M is the second mass, it's the bigger mass. So just whatever it takes for you, it's a product of the 2 objects you care about, okay? And so technically, you and the textbook that's in front of you, or the laptop in front of you, or the person sitting next to you, is there a gravitational force between those 2 masses? Yeah, but how come I'm not orbiting any of you? Because it's so small, negligible compared to who wins? The Earth wins, okay? So I orbit the Earth. Did you realize that? We orbit the Earth. It's just we have a very small radius, right? It's basic. When you stand on a surface, your distance from the Earth's core is the radius of the Earth, okay? Okay. Then divided by r squared. Y'all, sometimes that'll be d squared, just like the picture down below. So what is this r? What is this d? Now your gut instincts coming off rotation are radius, radius, radius. Maybe, maybe not, okay? I personally like the d better because I don't want y'all thinking it's always radius, radius, radius. It might, but it's not a guarantee. And so notice on the formula chart, what do they have? Find this equation, second column at the bottom. Is it r squared? Is it d squared? It's r. Look at what they say r indicates, radius or separation. And so really, y'all need to view this one as a separation distance. And I'm going to put in here center to center. It's not, if we're looking at the gravitational force between the Earth and the moon, it's not surface to surface, it's center to center, because the radius of the moon, the radius of the Earth matters. Make sense? Okay, so there's Newton's universal law of universal gravitation. It's not used just for close range objects on Earth. It's those long range distances, okay? And so let's take a look on the right-hand side. Now this one isn't super specific, so I'm gonna, make it work for us here. How does changing the, we'll say small mass and radius, because again, we gotta have two objects, small object, big object. If you want to make it the Earth and then maybe some kind of satellite. Okay. Do y'all know there's thousands of satellites orbiting Earth right now? Not just a couple. There's thousands. Okay. If you Google it, I don't even remember the number. It was way more than I was predicting. But then you keep reading, there's a lot of inactive satellites too that are just now space trash, right? They're no longer functional, but they just keep orbiting the Earth, okay? So imagine this, we're talking small mass as your satellite. How does this change coming up affect the force, gravitational force, and the acceleration? So, if this satellite is orbiting, what kind of acceleration is that? Little review time. What direction is our satellite orbiting? Not clockwise and not counter either. Not tangent. That's the velocity. Looks circular to me, right? Centripetal. What direction is centripetal acceleration? Always center seeking. And so we've got this center seeking centripetal acceleration, okay? And it's a net acceleration. So in the back of your mind, think about the only force acting on this satellite is the gravitational attractive force between those two objects. And so net force on the satellite is centripetal, would be capital F with a subscript, uniquely capital G. Because lower G usually indicates near range, capital G indicates that universal far range. And so you could I'm just going to keep it in terms of centripetal acceleration. We won't plug in v squared over r for this problem. And then that capital F capital G is the new equation. And so it'd be mass of satellite, and then mass of the Earth would be the big one. So notice I'm already getting away from 1 and 2 or little big. Y'all know I love subscripts. They should be your friends, okay? And then of course, all over that distance squared. R squared, yes. And so how does changing our satellite's mass, well, let's double it. Whatever the story, the mass of the satellite doubles. How does that affect the force on the satellite? It doubles. So the force doubles because one of the masses has doubled. We left Earth alone. And so distance was remain the same. Capital G is a constant. And so if one of the masses doubles, then you have a double force. But what about the acceleration? If you double the mass of the satellite, look at that last line there. Mass of satellite is on both sides. So it's the same. So acceleration would remain the same there. Everybody good? All right, reset back to normal mass. Now what if we have half the radius? And so if the radius, masses are the same, numerator is the same, but I have half the radius, what kind of force are we going to get from that? 4 times. Don't forget to square, and it's in the denominator. So, you know, a smaller denominator means a bigger force. 1/2 squared, 1/4. So it's going to be 4 times the force. What about acceleration? Now the mass remains the same now, but if my force is 4 times as big, then the acceleration will be 4 times as big. Okay. And then not that AP is necessarily going to do it often. Usually they only make one change at a time because they like to talk about the direct, indirect relationships. But what if you double the mass and the radius? Again, just double one of their masses. So we have a 2 on top. And then you double the radius. Don't forget to square. And so it's going to give us what kind of force? Half the force. And that double mass, so I've got 2ma equals half the force. That one's a little weirder, but what has to happen to the acceleration here? To get half the force, but your mass also doubles, 1/4. And so 1/4 the acceleration. Okay, now let's do a calculation. What is the force of gravity? Notice it's still saying force of gravity of a 2,000 kilogram spacecraft when it orbits 2 Earth radii from the Earth's center above the Earth's surface. Now I'm going to draw a picture here because there's, you know, be careful. There's the Earth. Here's 1 Earth radii. Where's our spaceship? 2 above the Earth's surface. And oh, wait, hold on. When it orbits 2 Earth radii from the center. Okay, so it's just 1 Earth radii above the surface. So yeah, read carefully. So I don't know. Here's our spaceship. There's our spaceship. Not an artist, right? And so the total distance separation, D or R, would equal 2 Earth radii. Now, do you have to have the Earth's radii memorized? Is it on the formula chart? No and no. And so here in our practice, you know, they expect you to look it up. AP exam, they would give it to you. Or honestly, here's what they would do. They would keep it in variable terms, okay? Because the new AP Physics 1 stuff, and I say new, 2015 it changed, but less time on a calculator, more time on the physics. That's kind of the gist now. And so 1 Earth radii, someone Google to correct me if I'm wrong, going off memory here. Oh, I know it's times 10 to the 6. Is it 3.98? Should have had this up and ready. Kilograms. Oh, meters. That's a good question. A lot of times they're stated in terms of kilometers or miles. So when you Google, if you Google, make sure you're with SI units. 6 million. Okay, so I'm going to go right now with just 6 times 10 to the 6, because 10 to the 6 is million, mega. And so to calculate F capital G, we get the mass of our ship times the mass of the earth. Ooh, we'll have to do know the mass of the earth. And so that one, I believe, is, I think I did I? 24th, okay. And over that D squared. And so G is that 6.67. Stay with me, everybody. Stay with me. I don't want to bang on the table because I'm tired of yelling. The mass of the ship, they told us, was 2,000. It's in kilograms. Mass of the earth, I gave earlier, 6 times 10 to the 24th. All over that distance of separation, I got 2 earth radii times 6 million meters. And then after you multiply by 2, don't forget to square. So this one, for calculations, be very careful with all the times 10. Can I highly recommend using the second button and then the comma button, okay? It's that capital E, but it's not the lowercase e function that graphing calculators have, okay? So to type this in, I would do 6.67, second comma, -11. That's your keystroke, okay? If you use the up caret, just be aware that sometimes, I don't know all the mistakes that are made. I think it's when you start squaring and parentheses, but if you just do up caret, somewhere along the way, students get the wrong answer. I can't nail it down. Okay, so something with arrows, but I'll tell you, for 20 plus years, I've used second comma, second comma, second comma. Works every time, all right? Someone get an answer? Now, if it was near Earth, we would get 2,000 times 10, right? So 20,000. What do we get on this one? Okay, so about 5,000, 6,000 newtons, right? Okay, so different. Near range, far range matters. Good deal? All right, we only get 2 more classes for gravitation. We'll talk about orbits next time and hopefully get into energy. Okay, it's going to go quick. Y'all are going to have to work with me. Hold on.